So you have your Beyond Labs worksheet that you need to finish. Shouldn't take you too long. And then we have our Electrochem Part 1 quiz. That's going to be on the exact same stuff as the Chem 101 homework Part 1, Electrochem Part 1. So like you're not going to have to draw like an electrochemical cell on it or anything like that yet. That's Part 2. Okay, so let's keep going on with our electrochemistry. So acids. So how to predict whether a metal will dissolve in an acid. And this is magnesium and hydrochloric acid, right? We all did that in 219 and, well, you would have done it in 219, but you definitely did it in 209 or intro chem, you probably did this one. So metals dissolve in acids if the reduction of the metal is easier than the reduction of the hydrogen. So I'm going to show you the picture or the reduction potential so you can see exactly what I'm talking about. So if the metals that you want to reduce are below the hydrogen reduction, then they'll dissolve in the acid. And that's like a single displacement reaction, right? Like exactly like, remember these? Like Mg plus HCl goes to, right? Remember this? Rolos, yeah, from forever ago. So anyway, those single displacement reactions or displacement. But if you've got nitric, because nitric has this right here, which is actually higher up on the table, you can dissolve, there's a lot of metals that will dissolve, there's a lot of metals that won't dissolve in normal acid, but they will dissolve in nitric acid. And so I'm going to show you the table. So this is that exact same table that I've been showing you again and again and again. And so you can see here, here's that She, right? The standard hydrogen electrode. So any metal that is below this will dissolve in acid, like hydrochloric acid, whatever, like that, right? But this is the special nitric reduction, right? So you can get a lot more metals to dissolve in nitric acid than you can in regular acid. And so that's why a lot of the times you'll see, that's why we have that nitric acid in the hood for your lab, right? So we have like hydrochloric, but we also have, if you can't clean your test tubes with a hydrochloric, then you use the nitric, right? Because the nitric can clean so much more because it's nitric acid. It's kind of our best of our best when it comes to dissolving metals. Okay, so any metal below here will dissolve in acid, but nitric can also dissolve these. All right, so now knowing that, which of the following metals will dissolve in acetic acid? And if they dissolve, what would the reaction look like? Okay, so when we do this, here's that hydrogen electrode. So anything below this will dissolve, right? So therefore, silver's above, so it's not going to dissolve. Copper's above, it's not going to dissolve. Iron, yes, it will dissolve. Chromium, there it is, yes, it will dissolve. And so then, writing the reaction, that's just writing like a single displacement reaction, right? So I'll just write iron for you so you can see it. We all know how to do this, right? So iron plus acetic acid, C2H3O2, it's just a single displacement reaction, right? So it's going to make Fe. I really hate writing acetic acid like this, but you know what? You guys are going to be in organic soon. I'm going to write acetic acid the way it should be written. That's the way you write in organic. That's how it should be written, right? CH3COOH. So those of you who are part, oh my gosh, CH3COOH. That's the way you should be writing acetic acid. And you'll see when you get to organic, that's the structural way to write it. And then that makes iron acetate. So that's going to be C. Because we're going to have 3 of them. I'm just going to write it like this. And then you got to balance it, right? And the reason, by the way, you write it like this, remember like our Lewis structures, everything organic is a Lewis structure. And it's because this is the way it looks like. That's its actual structure. That's why we write it like that. Anyway, those of you who have had me for a while know that I really hate writing acetic acid the wrong way. I don't like reading it like that, but it's okay. So here's the, oh, look, I have them right here for you. Here's the equations. They're just single displacement reactions. And again, so this is what happens when you put iron and acetic acid, right? That's your ions you get, or chromium and acetic acid, those are your ions you get, and those are all of our bubbles. Okay, so again, if it was nitric, all of these would dissolve. Okay, so now let's combine 3 different chapters of stuff. Yay! So we're gonna combine electrochemistry with thermodynamics and equilibrium. Yay! I won't make you make any ice tables though. Okay, so when you're doing this, we have 3 different equations. You do not need to memorize these equations. They will be given to you, right? So we have this equation, delta G negative RT ln K equilibrium. Oh, there's another K equilibrium. This here is the number of moles of electrons. I'm going to talk about, we sort of started talking about that last lecture. We'll talk about it more. And then this one, and then we're going to talk about that's Faraday's constant, which we'll look at in a second. And again, this is moles of electrons. Okay, so for a spontaneous reaction, we know that delta G is negative, E cell is positive, and K is greater than 1. Right? So our delta G is negative, our E cell is going to be positive when we add our 2 half cells together. It's always going to be positive, and K is greater than 1, meaning that the equilibrium lies towards the products. So we have a nice fun equation that we can write, 2 different equations. Again, we have RT ln K, or negative NFE. N is the number of electrons that's being transferred. So you know when we were balancing our half cell and we made the electrons, when we were balancing our redox reactions and we split them into half cells and then we made the electrons fall out, the number of electrons that you make fall out, that's your N. That's the moles of electrons that are transferred in the reaction. So that's where the N comes from. F is Faraday's constant, and it's just coulombs per mole. And again, you don't need to memorize that number. Okay, so let's practice with some of these equations. Okay, so here's our first equation. So we want to know delta G. So if we want to know delta G, we either have to use this or this, right? So when we go down, sure is nothing about a K here, right? So we're probably going to use this one right here. All right, NFE cell, negative NFE cell. And so we have our 2 reactions, and I put the reactions from the table right here so you could see. So those are our 2 reactions from our table, right? And then we have, here's our overall reaction. We need to decide which one's going to go where, right? So we just need to find our E cell and our moles of electrons. And then F is already given to you. Okay, so when we do this, here's our equation that we're going to use. E cell, we're going to find the exact way that we always write it. So if we look here, we have I2 over here, I2 over here. So this one's going to stay that way. BR2 over here is a product, but over here it's a reactant. So we're going to flip this, right? So we're going to have negative 1.09 plus 0.54. That's going to be our E cell. Any questions on that, just in case? Because we did this last lecture. I just want to make sure everybody understands what I just did there. So that's how we get our E cell. The next thing we have to get is we have to figure out the electrons when it falls out. So here's our E cell. I flipped the 1.09 and I left this the same, right? And then when you add them, you get a negative 0.55. By the way, E cell, this is negative. Is this going to be a spontaneous or a non-spontaneous reaction? Anyone?
Non-spontaneous.
Yeah, it's going to be non-spontaneous. Remember, for spontaneous, E cell has to be positive. So therefore, since this is a non-spontaneous reaction, is our delta G going to be negative or positive? Yeah, it's going to be positive. Yeah, very good. It's going to be positive. We should get a positive delta T here because our E cell is negative, meaning it's non-spontaneous. Okay, so now when you look at the electrons here, do you see how this one, 2 electrons, 2 electrons? So we're going to cross off 2 electrons just like we did in the half cell. And you can see it up here too, written the other way. Again, there's the 2 electrons. So you're just looking for, sometimes it works where it's already, like these are already easy to cross off, no multiplying needed. But most of the time, there's going to be multiplying needed. So our N is going to be our 2 electrons. Our F is our Faraday's constant. And our E cell was negative 0.55-ish. Oh, I have it right there. Perfect. And indeed, look, positive delta G. And this is exactly what we would expect to happen, right? Because since our E cell was negative, our delta G should be positive, non-spontaneous. So if it's non-spontaneous in the forward, we could make it spontaneous. It would be spontaneous in the reverse. Okay, so now I'm going to have you try one all on your own. Okay, so here's the reaction. F, I never remember F, sorry, F is 96,485. 96,485 coulomb per mole and negative NFE. Delta G equals negative NFE. That's an F. All right, that's all you should need, except for that's not a 5. That's all you should need to solve this problem. So the first thing you need to do is figure out which 2 potentials you're going to use, and then make sure the signs of the potentials are correct, right? Rearrange them. Then you need to figure out how many moles of electrons, how many electrons you have to cross off, and then you just plug it in. All right, so try this one, and then we're going to do it together. So I'll give you like 2 minutes. So if you're doing this now or watching this later, try this one, because it's got a lot of little minute details in it that you need to keep straight. And then we'll go over it in just a minute. Okay, how are we doing? Pretty good, hopefully, yes. All right, so first let's see, how do we figure out which ones we're going to use? Whoops. I2, there it is. There's an I minus, and there's an I minus. And then look at them, IO3. There's the IO3 right there. Right, so we must be using these 2 reactions. We just decide which way they're going to go. And so here we can see I2 is a reactant, but here it's a product. So this is going to end up being flipped, negative 0.54. This is forward, so that's just going to be staying as plus 1.20. And we just add these two, and those become our E cell. This is our F. Now we just need to figure out the number of moles of electrons. So you see here, you can do this by adding it, or you can just do it by inspection. So you see how this is 5 electrons right here, and this is 2 electrons? Well, we need these to be the same. So if they were the same, what number would we multiply the top one by? Yeah, 2. And that would give us 10 electrons, right? And then look over here, again, we're gonna need this to fall out, so we'd multiply this one by 5 to give us 10 electrons. So it was 10 electrons, that is our N. It's gonna just be 10 electrons, right? And so again, you can do it, again, just by inspection like I did, or you can do it much more deliberately. So I'm gonna show you it more deliberately here. So, and we just plug in those numbers. Oh, well, I guess here I'm gonna show it to you all at once because my animation didn't work there. Okay, so here's our first reaction, right? So we flipped this one to be 0.5, and then this one stayed the same. So when we added those two up, we got our E cell was 0.66. So our E cell is 0.66 volts. And again, if you have any questions on that, just let me know. This is sort of what we did last section. And then we look at the electrons, right? If we need these electrons to fall out right here, it's not lined up very well, but this one would have to multiply by 5, and this one would have to multiply by 2, and then you can see that this would be 10 electrons, it would fall out. This would be 10 electrons, it would fall out. So when we plug it in, negative N, we just had it was 10 moles of electrons, F, Faraday's constant, and the E cell that we just figured out. And when we saw this E cell, by the way, that it was positive, that means it's a spontaneous reaction. Remember, if E cell is positive, it's a spontaneous reaction in the forward direction. So therefore, we should get a negative delta G, and indeed, we do. We get a negative delta G, exactly what we were expecting. This is a spontaneous reaction under standard conditions. Now, again, how do we know it's standard? E cell. That means standard, so we must be under standard conditions. Standard must be under standard conditions. Okay, now let's try another one. This time, it says calculate K. Okay, K. I'm going to go back because I just don't want to give you the whole answer. Sorry if this hurts your eyes. We have two choices. Delta G's RTLNK or E cell, this one. Those are our two choices because they both have Ks. Right? So those are our two reactions. And again, these equations are going to be given to you, so you don't need to memorize them. You just need to know which ones to use when you're going to use them. In this case, we don't have anything about a G, so we can't use anything with delta G on here or anything because we don't have G. And the question says we want to know K in this case. Well, this is the moles. We can find out that. That's not hard, right? This is just a constant. It's always the same. And we can just solve for K and we can calculate E cell, right? And so if we look at this, by the way, I'm just going to leave this here so I can write down here. Here's the two reactions according to this. So I just took them from the chart. I left this here intentionally. What's the voltage of the She, the standard hydrogen electrode? A lot of times they don't give you that voltage. So you should sort of know what the voltage is. Remember, it's the voltage everything is measured against. So that voltage of the She is, if everything is measured against it. Anyone? Yeah, 0, right? The She is 0, right? And so again, the She is how we got all the voltage, because we can't measure the voltage directly. So we chose She to be 0 and then measured everything against the She. That's how we got all of our voltages on our reduction tables. Okay, so now if we look at this one, we can see H plus is a reactant. H plus is a reactant. Well, so 0 is 0, it doesn't really matter. And if we look here, Cu is a reactant, but we need this to be a product. Or you could have looked at the solid, whichever way you want to do it. Both of those would have worked. So that means that this needs to flip to negative. So this is going to be negative 0.34. So that's going to be our E cell is negative 0.34, right? Again, because we had to flip it, our reduction is going to be 0 no matter what, right? And then when we add those together, here is our E cell, negative 0.34. And again, our N is just the number of moles. And in this case, it's easy to see. We don't need to do any multiplying. It's 2, right? Pretty easy to see. You wouldn't even necessarily need it. I just wrote these for you to make it easier for you to see. So now all we do is plug that in. Pretty simple compared to the stuff that we have been doing. All right. So I plug that in. Right, so if we're going to solve this, I'm just going to move it over on the other side. We're going to solve for K, right? So you have, right, log of K equals, and then if we plug in your E cell, negative 0.34 volts, and then I just flip these over, 2 over 0.0592, right? So then you end up with E to the whole ball of wax, right? And again, however you want to solve this with your algebra is totally fine with me. If you want to solve it in more steps than that, that's fine. But basically, we're solving for this. And remember that log is your second function E, which we've already done a couple of times when we were doing equilibrium. So you should be pretty good with this. So when you solve this, you end up with K is 10 to this. And so here we are. We get 3.2 times 10 to the negative 12. And I mean, not E, I should have said 10 to the X, right? It's the second function log, not natural log. That was my bad. It's not this ln log. It's the log, second function log. So hopefully, I think I wrote that backwards on there. Okay, so when we get this, 2 things to note. Our E cell is negative, meaning that, is it spontaneous or non-spontaneous with a negative E cell? That's my question. Spontaneous or non-spontaneous?
It'd be non?
Yeah, non-spontaneous. Yes, so it's non-spontaneous. And so therefore, we would expect a really small K, right? K is going to be much less, or just less than 1. That's all we know, is that K is going to be less than 1. And indeed, look, K is less than 1, meaning at equilibrium, right, it is reactant favored because it didn't go spontaneous in the forward direction. It stayed almost in the reverse direction. And so in this case, we would expect what would we expect our delta G to be here? Would we expect it to be negative or positive? What do you think? Would delta G be negative or positive in this case? Seeing a few. Yes, it would be indeed positive, right? This would be a non-spontaneous reaction. So it would be positive. Okay, let's try another one. So we've already done this reaction a couple times. So this time we're gonna calculate K for the same reaction that we did. So we're gonna use the exact same math we did before, deciding which 2 we're gonna use. And so on your exam and your quiz, when you take this, I'm going to give you like a piece of a reduction table. I might even give you a giant reduction table. I'm not sure. But you just go and you find the reactions you're going to use. IO3 is unique, so we'll use IO3. We've already done these two before, so when you look at the electrons, we already know that the N is going to be 10, right? Because those are the electrons that are going to fall out. We just need to decide if it's, we just decide our E cell. IO3 here is a reactant, it's a reactant, so this gets to stay that way. I2 is a reactant, but here it's a product, so it's going to be negative 0.5. And then we just add the 2, plug in the 10, and that's the whole problem. Okay, so again, this is going to be 10. I didn't add those, let me see. When we do that, so we have 1.2 minus 0.54. So that's like what, 0.66-ish, right? I think I just give you the answer. So that's our E cell. Our N is 10, and we're just going to solve for our log of our K. Right? Oh yeah, I have it right here. And again, when we look at these, this one's 2 and this one's 5, so our total moles are going to be 10 electrons. That's what's going to fall out. So that's what our N is going to be. And I want you to try and put this one in your calculator for me. I need you to all do this because this could happen on an exam or a quiz, and you're going to see why I want you to put this one in your calculator. Okay, so when you put in your calculator, so solve this problem. Please solve this problem. So you have 0.66. Actually, I'll just put it right here. 0.66 equals 0.0592 over 10 log of K. So I need everyone, if you're doing this now or if you're doing this later, solve this problem and put this in your calculator. And yeah, y'all need to do this because you could see this happens. So you need to see, I want you to see what your calculator does. I see a few people have already solved it. What was that?
It gives me a math error.
Yeah. Yeah.
Is it too big to calculate?
Mm-hmm. This number is too big to calculate in your calculator, and this happens. So this is like the super duper crazy spontaneous reaction, right? And it's so big, your calculator can't even calculate it. So in that case, you just simplify it as far as you can. And so literally your answer is 10 to the really big number. I can't put it in my calculator because my calculator says error. Right? So if you see that, and this happens because if you've got a crazy spontaneous reaction that lies so far to the products that you can't even calculate it. So I want you to know that this can happen. So be prepared. This can happen in your calculator. And then you just write it as simple as possible, or just know if it's a qualitative question, it's a super spontaneous reaction, right? It's like super spontaneous reaction. So then your delta G would be negative, right? So if you do see in a problem that you get calculator error, just know it's probably because the number's too big for your calculator to actually display. Okay, now, next we're going to talk about some really fun stuff. So we're going to look at, so we've been looking at everything at standard, right? At standard concentration, everything is 1 molar, but what if it's not 1 molar, right? And we don't always do everything at 1 molar. So we need to look at what happens when it's not 1 molar. So we know there's a relationship between Q, remember Q is when it's not at equilibrium, and the equilibrium constant, and delta G, right? We did that one last chapter. And this one you can really just use kind of, I'll show you how you can use this one in your brain just in a few minutes. So if you change the concentration of the reactants, it's going to affect your delta G. So if it's not 1 molar, it does affect which way it goes, and it does affect your K also. So because delta G determines the E cell, the voltage of the cell, the voltage will be different than if it's 1 molar or if it's not 1 molar. Okay, so let's look at a picture of this to explain all of this. Here's what we've been doing. right? 1 molar, 1 molar, right? And here's our voltage. Now, if you look at this here, our second one, now this one is less concentrated, and this one is more concentrated, right? So if we look at this here, look at our voltage is actually more. That means more electrons are headed toward that cathode, right? Now, the question is, how and why does that happen? Answer, entropy, right? So and we loved our entropy last chapter. If we look at here, this one is a less concentrated, right? Meaning there's more possible places, right? This is a happier one, right? This is happier. This one is more organized, right? Not as many places for these ions to be in this one over here. And now, how can these, so what happens, they want to hit equilibrium, they want to become the same in the end, right? How can we make this one over here much happier? Right? So if you think about entropy, so what usually happens is people go, oh, this one's going to go over here to even it out. But that's exactly the opposite of what entropy is, right? Entropy means it's going to go from high potential energy to low potential energy. So what's going to happen is the less concentrated is actually going to go over here to make this one less concentrated, right? So it's actually going to come over here to even itself out. Sort of like what you guys, kind of like what you talked about in 219, if you ever talked about osmosis, sort of kind of like that. So you have this less concentrated is going to flow over here to the more concentrated until they're equal again and they're at equilibrium. So until then, you're going to have a higher voltage, because in order for these to become the same, or for this one to become less concentrated or happier, or a lower entropy state, right? More microstates, happier. This one has more microstates because it has more places it can be. What's going to happen is this is going to have to be reduced, because it's going to have to be going from, our electrons are going to transfer over here, and we're going to have Cu2 plus going into our copper solid. Right, so we're actually going to make it even more than it was before. Our electrode, our voltage difference will be even more than. Okay, so let's look at this in way more detail. So this is the Nernst equation. Here's how you derive it. You don't need to know how to derive it, but if you're interested, it's kind of interesting how this works. It's pretty simple. We just combine two equations, NFE and RTLNQ. Remember RTLNQ from last chapter and then NFE from this chapter? We just combine the two. So in this case, you have your E cell standard. So this is when they were at 1 molar. And then you have that same piece, and then instead of K, you have Q here, right? Because it's before it's at equilibrium. And this is how you can find your E cell not at standard conditions. So this is another equation. You do not need to have this memorized. You can always use this equation. But this equation is used when you're not at standard conditions. Okay, so a lot of times people are like, how do I know if I'm standard conditions? I think I've said this 1,000 times now. You're looking for that. So for example, when you see this problem, it's missing it. It's not here. So that's how you know you have to use the other equation, right? Because it's not there for us. Okay, so now if we look at our problem here, I just pulled out the equations from, I didn't pull it out very well, from our little chart that we've been working on. And you can see here again, I just like pulled these out. By the way, by looking at this, see if you can do this now. How many moles of electrons are transferred in this reaction?
It'd be 6, huh?
Yeah, 6. Do you see how fast you can see that now? So again, You can solve these much faster than I'm solving these, but that's your N right there. You can see that one, this one's going to be by 2, that one's going to be by 3, 6 moles. Easy peasy. You can see it when you look at the half reactions. You can't really see it from your balanced reaction. It's very difficult. You need to go onto the table. You need to go back to the table to find that N, because it just pops out at you once you get good at it. And then again, to do your E cells, right? That's not hard either. Reactant stays the same. Product, reactant, flips. Right, so you can get your E standard easy, and you already know your moles, right? Okay, so now, here are, I need to give you these reactions just based on that picture. So here's you need this, right? Because, right, you can't find K without these. So if we want to find our K, we need these in here to find our K. Okay, so now, and again, I want to remind everyone, find our Q. That's a solid, that's a liquid, that's a solid. So they don't go in our Qs. A lot of times I have these problems on like quizzes and people are like, I couldn't find my Q because you were missing these. No, remember, solids and liquids do not go in Q. Only aqueous is in gas, right? So when we do this, we already found our E cell. Well, we just need to add it. We have our N now, and then we can just plug in our Q, right? And again, just in case you can't see that, how that 6 electrons, how we got it. So here's this first reaction, and here's our second reaction. I flipped it over. So this, again, this is straight from the table. So you're always going to be getting this data from the table. Usually I'm just going to be giving you a table, and that's where you're getting your data from. So this is straight from the table. So we flipped the equation to make it match. So we had Cu on this side and Cu on the side. So we flipped our potential. This one was already good. This one we had to multiply by 3. This one we had to multiply by 2. So our electrons would fall out, and there is our E cell. So we have a piece of our reaction. So that's our E cell, 1.34, 1.34. Our N is 6. So now, when we do our Q, remember Q, products over reactants, right? So we have our products, which we have a balanced chemical equation on here. Where do I have it? Right, products over reactants. Just erase this. So we have Cu2 plus over Mn times our H. I don't know if anybody knows, but this isn't balanced up here. My bad, I wrote an unbalanced equation. I would fix it right now, but I'll never get back into Zoom, right? So when we do this, remember, it's going to be Cu2 plus raised to the third over Mn04. This is not, obviously, I did not balance this reaction very well. Everybody see how unbalanced it is? I need to balance this reaction better. So when you do this, we get, I finished it at 1.14 volts. This is what I got. See if you got the same thing. I'm not trusting my balanced reaction right now. It must have happened something when I typed this. See if you get the same thing. I'm going to check out the balancing this reaction while you guys put that in your calculator. Yeah, I have this as a 2. So I'm going to agree that there should be a 2 here, not a 3. Anybody else? An agreement on that? I don't have my calculator with me, but I'm pretty sure that should be squared and not cubed. Yes. Okay, so when we finish this one out, here's our new E cell. And that is, again, at non-standard conditions. Okay, so let's try another one. And we'll check our balancing before we do this one. Okay, so I want you to try this one. I'm balancing it as I look. Not super balanced. Oh yeah, we're good. Okay, all right, so I want you to try this one, and then we're gonna go over this one together. I'm not gonna help you with anything except for its E cell. There's no standard, oops. There's no standard here, okay? So try that, and then we're gonna go over it in just a minute.
Can I see the answer for that last slide just really quick?
Sure, let me just go back. I got 1.41.
Okay. I did. All right.
Oh, Adrian, you got 1.45? Okay, that's perfect. Okay, here's the next one. Double checked, this one is balanced. How are we doing? Are you ready, or need another minute? We all ready? Yeah?
Could I get like a minute more?
Yeah, sure. Give me another minute. Hey, how we doing? Good. Waiting for a couple more. Okay, so this is the same. I think you guys have already memorized what this E cell is here, right? So I think what is it, 0.66, because we've done it so many times now, right? And then if we look at our N, we already know our N. Our N is 10. So we just need to plug it all in and then solve in this case. So, and the ion concentrations are all 0.1. So as a reminder, doesn't count, right? So you've got no products in this one, and these are all 0.1. So it's 1 over all of those. Okay. So when we do this, we get
we also get the 0.1 or not? Hydrogen is just 1. But ion, I mean.
Oh, it's AQ, so it counts.
Okay.
Yeah, because it's AQ, it does count. It's just the solids and the liquids that don't count, but any of the AQs do count. Okay, so our E cell, we already done that like 6 times, and we already know our N, right? So when we do our, I'm just gonna do the Q here because it looks really weird, right? So our products, which are none, so 1 over, because we have no products. And so we have, it's going to be IO3 minus squared. I'll just do this because I know it's been a little bit of time. H plus to the 12th. I minus to the 10th. So your Q ends up being 1 over, I know this is so weird, 0.1 squared times 0.1 to the 12th times 0.1 to the 10th. That's your Q. Weirdest Q ever, but that's what your Q is, right? Because we have no product. So just 1 over all of those. Okay, so after you get your Q, so then you just have your E cell, which is 0.66. That's not what I meant to do, right? 0.0592 over, our N was 10, same N, and then it's going to be log of that crazy huge number right there, log of that whole thing. So when I did that, I got 0.52. So I think the hardest part of this one was the weird Q, very strange looking Q. We have some weird Qs and weird answers when we do these problems, just letting you know, we do get weird answers. So we get 0.52. Okay, any questions about this one? No questions? Okay. Just making sure we have time to write that down. So now we're going to look at more what I talked about before when we're going to look at the concentrations of the cells and when they're different. So we can get a spontaneous reaction when the oxidation and reductions are the same. So if we have the same reactions, we can actually create a voltage from it by just using different concentrations. And again, this is going to be due to entropy, right? The more concentrated solution always has a lower entropy than the less concentrated. So the less concentrated will always go towards the more concentrated. So this is sort of what we were just talking about before. So the electrons will always go from the less concentrated to the more concentrated because it's trying to even them out. So the oxidation of the electrode in the less concentrated solution will increase the ion concentration in solution. We're going to talk about it in 1 second. The less concentrated in this case would have the anode. The reduction solution ions in the electrode in the more concentrated will actually reduce the ion concentration. And again, the more concentration is the cathode. Okay, so again, the electrons are going to flow from less concentrated to the more concentrated. And the oxidation, the oxidation of the electrode in the less concentrated solution is actually going to go to it increases the amount of the ions, and the more concentrated will go to reduce the concentration. I know it's a lot, but I'm going to show you a picture. Pictures work better. Too bad I can't do this all at the same time. Okay, so here we are. You can see we have the exact same thing. Copper, right? So we have the exact same thing. And right now, they are the same concentration. So we have no voltage because they're at perfect equilibrium. They have no weight. There's nothing driving this reaction. So when these concentrations are equal, there's no difference in the potential energy. So nothing happens. But, and again, look at 1 molar. But let's change the concentrations. So if we change the concentration, so now all we did, we just increased the concentration of this over here, and we decreased the concentration of this one over here. So when the concentrations are different, the electrons flow from the side with the less concentrated solution, that's our anode, to the side with our more concentrated solution, our cathode. And now let's look at what happens in that case. So the electrons move over, but let's look what's happening to the solutions themselves. So this one is less concentrated over than this side. So if this one goes over here to Cu2 plus, it's actually going to increase the concentration of your Cu2 plus in solution. Where this one over here is going to take the Cu2 plus out of solution to make Cu solid. So this one's going to become more concentrated. So when the electrons are flowing over here, this one's become more concentrated because we're actually increasing the concentration of Cu2 plus. And then if we look at our cathode, at our reduction reaction, this one's actually decreasing here because it's making more Cu solid. And so it's trying to, it's like a Le Chatelier's problem. It's just in 2 pieces, but it's like Le Chatelier's. And so in general, when the concentrations are different, the electrons will always flow from the less concentrated, to the more concentrated side, right? And their ions will end up in the end being the same, and then we won't have, and then when they're the same, when they get back to equilibrium, we're gonna have this, back to 0. Nothing's gonna happen once they get back to their original concentrations, or not the original concentrations, when they get back to the same concentrations. Okay, so now if we were going to draw this cell notation. I think I have this for you. So this is just a little caveat to drawing those cell notations. So we still do the same thing with our anode, and I'm going to put the solid here, right? That's our line for our electrode. And now in this case, our Cu2 plus, we need to note that the concentration, and this is aqueous, we need to note that the concentration is the difference. So you just do like 0.10 molar, 0.11 molar. Salt bridge, and then our other one is also Cu2 plus, AQ, and this one's 2 molar. Electrode, Cu, solid. So if you do have different concentrations, you show those different concentrations by putting them after your ion. So that can happen, and that's how you would show, because otherwise, if I didn't put that in here, look, you'd be like, Dr. McAdam, nothing happened. This is exactly the same on both sides. So you have to put in the concentrations. There we are, much prettier. Okay, so this concept is really hard to do on your own. So does anyone have any questions? I think this is the hardest thing with our brains to make this work. So I want to make sure if anyone have any questions on this stuff. Does it make a difference the side the concentrated goes on? No, it's always going to go from less to more. So if this one became constant, if like, let's say that this one was the concentrated side, that this would now be the cathode. And if this was the less concentrated side, this one would be the anode. That's supposed to say anode. It doesn't matter what side it's going to be on, because it will always go from less to more, like always, like it's always going to do that. Does that make sense? I know with the picture, it doesn't really make sense, but yes. And again, this I think is one of the most difficult topics to understand. I should say one of the most difficult things to do on your own. So any questions before we go on this one? Go to the next piece. We're good with concentration. Okay, so we're going to spend, I'm not really going to talk about batteries that much, but I want to make sure you read that in your book, because your book just kind of goes through the batteries. But I wanted to talk a tiny bit like fuel cells, because we actually have these, like, right? We have hydrogen cars. This is how a hydrogen car works, right? Like the Toyota Mirai, and I don't know, there's a bunch of hydrogen cars, right? They actually work like this. And so I wanted to take a little minute doing this. So how these hydrogen fuel cells or these hydrogen cars work is, instead of gas in your gas tank, you fill your gas tank up with hydrogen. Like literally you fill, now let's think about that. How do you fill a gas tank up with hydrogen? Hydrogen is a gas. How do you make hydrogen a liquid? Crazy high pressure, crazy cold. Right? Really high pressure, really cold. It was actually when they first released the Mirais, the Toyota Mirais, they had a problem where the fuel handles would freeze to the car, and you couldn't get them out of the car. They would stick in the car because they were so cold, and they had to like develop different types of plastics and different types of like, they're not even plastics, they're like crazy silicone compounds that wouldn't freeze at like, I can't remember, it's like it's cold, it's like minus 200 or something like that. Okay, so you fill your car with hydrogen, and the oxygen obviously just comes from the air. And what happens is the hydrogen and the oxygen come together and they make water. That's like the simple thing. Now let's look at the little fun part of it. So here's the hydrogen coming from the gas tank, or the fuel tank, and here's the oxygen coming from the air. And now what happens is the anode and the cathode, in this case, it's a redox reaction. This is literally an oxidation reduction reaction occurring in the cars. So the anode and the cathode are both platinum, so they're both the inert electrodes. The electrolyte solution in this case, because you got to have an electrolyte, right, because we have to even out those ions, is the OH minus. And the anode, you can see here, you have your oxidation of your hydrogen, right? And then at the cathode, you have the reduction of your oxygen. right? And in this case, what we're doing is we're actually making water. So like when we do this, it's like literally, I don't know if you've ever been behind a Toyota Mirai, but they like literally let their tailpipes, water comes out. And this releases tons of energy, right? And so with these fuel cells, you actually run the cars based on an oxidation reduction reaction of hydrogen and oxygen. And so, and the byproduct of this ends up being water, which is actually super cool. Okay, so those are our fuel cells. Just want to talk to you about that for just a second. Okay, so now we're gonna look at, so far, what we've been talking about is electrochemical cells, right? Or voltaic cells, right? So voltaic cells, when we've been talking about, it's when we talk about how it's spontaneously, right? The voltage is spontaneous if it's positive, and you just rearrange, you take your reduction reaction, your oxidation reaction, and you rearrange them, just like we talked about. This one goes forward, the one below it goes backwards, and then you pair them up, they produce a voltage, right? And in this case, if you've noticed, we always say that the anode has a negative charge and the cathode has a positive charge, although we don't really talk about the charges, and I'm not worried about you knowing the charges, like that the anode is always negative and the cathode is always positive. But this is what we've been talking about with our voltaic cells, right? Now, in electrolytic cells are when we have an oxidation reaction and a reduction reaction, but when we pair them, it's not positive. It's actually negative, but we still force the reaction to happen, and we force the reaction to happen by adding energy to it. So often, which I did not ask you guys this last chapter, but almost every single thermochemistry exam, thermodynamics exam I've ever had, the last question is, how do you make a non-spontaneous reaction spontaneous? And I stopped asking it because nobody could get it right. The answer is you add energy to it. If you add energy, you can make it occur. Okay, so let's look at these electrolytic cells. Okay, so here's what we have been talking about, voltaic cells. Okay, so in our voltaic cells, if we look at our reaction, right, we have our oxidation over here, lose, right? And then we have our reduction over here, right? And then we have, right, reduction happens at the cathode. Remember, Leo the red cat goes grr, right? Well, now, an electrolytic cell, look over here at our anode, right? In this case, we had copper going to copper solid. But what if I wanted from copper solid to go to copper 2+, right? And instead of zinc going to zinc 2+, I want it to go backwards, right? This is non-spontaneous. If we added these up, we would have a negative E cell, and you'd be like, no, right? If you added these up, you'd actually have an E cell. It would be negative 1.1 volts. Just believe me, I'll show you why in a second. That's if you added these two reactions up, just like we've been adding these reactions, you would have a non-spontaneous reaction. But if we still want this to happen, we can do it. We just have to add more than 1.1 volts, and then we can get it to happen, right? So if we just add more than 1.1 volts, we can make this go backwards. So we can force this to go backwards. And that's what an electrolytic cell does. It forces a non-spontaneous reaction to happen. And it does that by adding energy through some sort of a voltage source. So hooking it up to a battery, right? It needs a voltage source, and then you can force it to go backwards, right? And some people are like, well, why would you want to force it to go backwards? Oh, you can do so many fun things making it go backwards. So, for example, you can do this, which this is actually super fun. Usually we would do this. I do this with pencil lead, which even makes it more fun. You can split water, right? Using electrolysis. We can split water. We can break it apart. We can electroplate things. Remember we talked about how if you have like a silver ring that's like coated, like it says like coated in, silver or coated in gold, that's all been done by electrolysis. So electrolysis is actually really fun. You can also, let's say we have a compound, like a really cool metal that we like, but it's bonded to like some other element, and we want to get that metal, we can use electrolysis to split it apart. So you can do so much stuff with electrolysis. And so what we're doing is you're going to see this, we can actually break and we can actually separate the elements. And this one's really fun right here. This is just water. This is how we separate water. Okay, so now, electrolysis, again, uses energy to overcome the barrier of a non-spontaneous reaction. And so it's the opposite of spontaneous. So for example, if you have hydrogen and oxygen, it will spontaneously become water. But if you want to separate water, you need to add energy, right? And that's electrolysis. And again, what fun things can you do this? You can do metal extraction. We're going to talk about how we do that, and metal purification. This is huge in manufacturing. We can produce hydrogen for fuel cells. This is actually an idea. So right now, the biggest problem with those hydrogen fuel cell cars is where do you get the hydrogen? Right? Oxygen is easy. It's in the air. Hydrogen, not easy. And so an idea is if we can use electrolysis and pull the hydrogen off of water, we can use that for fuel. Unfortunately, that takes way more energy than using the fuel cell itself. So it's like a negative net energy, not really an option right now until we can figure it out. Actually, somebody figured out a genius way to do this like 2 months ago, so we might be able to do it. Right now, we pull these hydrogens off hydrocarbons off fossil fuels. That's where we get the hydrogens right now. But pretty soon, we're hoping we can do it like this, because that would be incredibly clean energy. And the last thing is metal plating. Okay, so for these electrolytic cells, again, you have to have some kind of power current. And then again, you have to have more voltage than it actually predicts. So let's say that your voltage was negative 1.1 volts. You need to have more than, right? So you need to have greater than. That's supposed to say greater than. Your voltage needs to be more than that. It needs to be a bit more than you started with. Okay, so don't really worry about these pluses and minuses. I'm not going to make you worry about those. Just know that they're the opposite that you have been seeing. So again, the electrolyte in this case is usually going to be a salt solution, or sometimes it's a molten ionic salt, and we'll talk about those. Now the cations in the electrolyte, the positives, are attracted to the cathode, right? Because the cathode is the place, same as we did before with our salt solutions, right? The cations are going to be attracted to the cathodes because that's where the electrons are going to, and it wants to keep it electrically neutral. The anions will be attracted to the anode, again, because the anode is becoming positive, and so, of course, it wants to equalize it. Okay, and so then the cations that pick up the electrons are going to be reduced, and the anions to the anode are going to be oxidized. So let's look at what that means. Okay, so a lot of times these electrodes are going to be graphite, and the cations, so like, I'm just going to say Na because we're going to see it in a second. So Na, like cations, are going to be reduced at a cathode to the metal element. So they're going to be reduced, Na plus, right, to Na. Let me just put the electron on here so you see it. So they're going to be reduced at a cathode to their metal. And the anions are going to be oxidized at the anode to the non-metal element. And so this one would be like, well, you could do it with Cl. Okay, so let's look at a picture of this. This is with our water, right? So here's our water. In this case, we have our anion, And this is making our oxygen bubbles and our hydrogen gas. And so you can see here's our cathode making hydrogen gas. And here's our anode making oxygen gas. And we had to hook this up to an external power source because if we looked at our reduction potentials, this is a non-spontaneous reaction, right? It should be the opposite way. And so we have to add energy in order for this to occur. Let's look at the NaCl because that one's actually kind of fun. Okay, so here's NaCl. So you can see here, here's our anion. Here's our cation. So what's happening here at our cathode is our anion is it's gaining electrons and it's becoming Na solid. Our chlorine, you can see here, our chloride ion is actually being oxidized into our Cl2 minus. Now, why do we do this? This is how we get sodium solid, right? So you might have seen this in 209. We actually put the sodium in the water. Hopefully you've seen a picture of it, and it burns and like flames all around the water and jumps around. If you saw this in intro chem, how do we get the sodium solid? We get it in this exact method right here. And so in this time, our electrolytes here, it's just molten Na. It's like NaCl plus, and so molten NaCl comes apart into Na plus and Cl minus. And so these are just flying around in the solution, right? You just have NAs and Cls, and then you have an inert electrode. Usually this is graphite in this case, but yeah, it's usually going to be graphite in this case. And so what happens is the Cl minus are attracted here, right? And then they're changed to Cl2 minus gas. Our electrons always go to our cathode, right? They're always going to go to it's still LEO goes GER, that doesn't change. And so here's our cathode. It's still gaining electrons reduced. This is still losing electrons oxidized. That never changes, right? In this case, what's happening here, these electrons that are coming on over here, and Na, oops, and the Na, these two go together and they make Na solid. And so you actually end up having Na solid plating this electrode. And it's kind of cool because Na solid, if you put it in water, it literally burns. So you can't do this in water, right? That would be bad. That's why we use molten NaCl, because you can't do it in water because Na solid literally burns. It literally is on fire in water. Okay, so that's NaCl. The next one, we'll just do this one and then we'll stop, is electroplating. This is if you have any kind of like 14 karat covered ring, right? Gold ring or sterling silver coated ring or silver plated ring or gold plated ring. If you've ever heard of those, this is how they do electroplating. And what electroplating is, it's just putting one metal on top of another metal. So what's happening is they put your ring or your necklace over here, and this is our cathode. So your ring or your necklace is hanging at the cathode. And what's happening is you have ions. So they just put this in a solution of silver ions. So it's just silver water, really just silver water. And then we have the cations. So again, we have ions. These are silver ions. They're just hanging out, chilling out in our reaction. And the cations are reduced at the cathode. So they go from Ag plus to Ag solid. And again, we have to add a voltage for this to happen. In the anode over here, this one is going to be a silver electrode. And that's our Ag plus, again, is going to come over here. We're going to make more of these Ag pluses. And this is going to be oxidized. So it's losing electrons. Again, here's our electrons going over to our reduction at the cathode, right, is still occurring, and the anode oxidizes and it replaces the metal cations in the solution. So as this occurs here, so this goes from Ag to Ag plus, and then the Ag plus grabs these electrons here and creates Ag solid coating the ring. And this is what happens when you have a silver-plated, silver-coated ring or necklace. We literally will take these silver ions and change it into silver solid on a ring. And this is what electroplating is. And you can actually calculate the mass of the silver that has plated this ring. And we're going to do that next time. Okay, so that's just a little bit of the use of what you can do with electroplating. Next time, we're going to talk about the crazy intricacies of electrolysis. Electrolysis is harder than voltaic cells. So I highly suggest voltaic cells have been what we have been doing from 20 minutes ago to the beginning of the chapter. It's all been voltaic cells. Electrolysis, that's when we're adding the voltage. That's a little trickier. So if you haven't read in your book about electrolysis before Monday, go through your book on electrolysis because it can get trickier, especially when we're mixing ions and doing all this other crazy stuff. Okay, so look in your book about that one. That's all we have for today. Does anyone have any questions? Hydrolysis is just specifically talking about water. Electrolysis is anything, but same type of thing. Yes. Okay. Any other questions before we go today? No? So make sure you take your quiz. Your quiz does not have anything like this on it. It's just on the Chem 101, Electrochemistry Part 1.